We are slowly reaching the last bits of our topic on torsion, and I'm not going to let you go without the last spark of amazement. What we are going to discuss in this topic are essentially torsion of thin-walled members, and we will learn a very important concept there on the shear flow. Then we are going to move ahead and we are going to talk about stress concentrations in an exactly similar way we talked about the stress concentration in the axial loading case, where you have sudden discontinuities, how the stresses peak up in those regions. And lastly, I'm going to leave you with some future reading material. If you're interested, you can take a look into that one. So let's go ahead and dive in on our very first topic, that is the torsion of the thin walled members. Now, before we go into the torsion of the thin walled sections or the thin walled tubes, what I want you to do is that I want you to first recollect what we have studied, right? So now if you see, suppose you have a shaft, right? So let me maybe draw the shaft over here, where say in this shaft, say the shaft has a cross section. If I take a look at the cross section, suppose it is a circular cross section. So this is, say, this cross section over here, it is a circle, nice and round, and here I am coming and I'm applying to the shaft, I am applying, say, a torque, right, equal and opposite torque. So it's a balanced system, right? Now, what we have studied until now are these solid shafts, right? Solid circular shafts. The circular is more important. Now, if on this circle that you see, if I take 2 points, say this is the center of my circle, somewhere around here, and if I take any 2 points on the circumference, let me maybe pick a point B over here and pick maybe another point C over here, both of which are of course equidistant from the centroid with the radius, say, r. What we have learned is that since each of these points are at the same distance r from the center, I am going to have my tau, that is the shear stress at B, must be equal to my tau at C, 2 points at the extreme periphery, right? Now this is true because your R at B is equals to the R at C, which is equals to the radius of the circle. As opposed to this, let's consider another shaft, prismatic. Remember, mind you, it's prismatic. It is prismatic in the sense, and if you recall our discussion on prismatic sections, it has the same cross section throughout, right? And suppose that particular cross section, which is same throughout, is now this one. It is not a circle, it's a non-uniform cross section, but it is same throughout, right? So it is prismatic in that sense, but the cross section itself is not a regular circle, not a regular rectangle, maybe a kind of an odd shape, something like this that you have over here. Now if for this shaft that I am looking at right now, if I'm applying torque, balancing torque at both the ends, say T over here and T over here as well, and if I take another set of 2 points, let's say point B and another point C over here, and for this irregular cross section, let's say my centroid is somewhere over here, right? Now for this shaft, which has a non-symmetric, it's a non-circular section, and let's say the points, the distance of the points from the centroid, let me just mark them, are RB and RC, which is of course different than the R that you had previously, and they're not equal. So in this case, my tau B will not be equal to my tau C. Why? Since my RB is not equal to my RC, right? So let's have this concept first ingrained in our memory, that if I am looking at a section which is non-circular, although if I'm applying equal and opposite torques, if I take 2 points on the circumference which are not equidistant from the centroid anymore. They have two different distances, RB and RC. The shear stresses which are developing as a result of the applied torque at both the ends are not going to be equal, right? Now, once we understand this, let's go to some interesting discussions on thin walled tubes, right? So for the thin walled tubes, I'm going to present to you this figure over here. Okay? So let's try to understand the figure, and then we will go into the derivation and discussion on a particularly important item, that is the shear flow. So what you have is a thin walled tube, something like this. A practical example of this may be something like this. You have a thin walled tube and it's non-circular, right? So if you take a look at this cross section over here, it is not a circular cross section. I sort of bent it over here. So it is a non-circular cross section that you're looking at. Okay? Now in this thin walled tube that you have over here, suppose you take at in somewhere from the left end to the right end, if you are taking a small element of thickness dx and you are isolating this element over here, that is A, B, C, D, and you are essentially taking out this entire cross-sectional segment, and if you are portraying it over here and you're assuming the wall is thin, that means that your shear stresses across this thickness over here, remember when we're looking at the solid shaft, the shear stress is maximum at the exterior and minimum at the particular centroid point that we have, right? So in this particular case, if we are looking at the shear stresses, how does that look like? If I'm looking at the shear stresses, it is something like this over here, right? So since this is a thin wall, right, it's a very thin, and say the T varies, right? If the T varies, and suppose here my thickness is say TB, and at this particular point my thickness is TC. And as we learned from our discussions in the couple of pages before, since this is a non-circular cross section, my points B and C are at two different distances from the centroid. So here I am going to have a particular shear stress tau B. Here I will have a particular shear stress tau C over here, right? And in between I will have the transition, because remember this tau B that you see over here is actually the same across the line. So if you go ahead and if you draw, say if I go ahead and draw say one line over here, all across that line, all across this line, I'm going to have tau B. Similarly, all across this bottom line, if I am going and drawing this one, I am going to have the tau C. So in between you must have the transition from tau B to tau C. So it's tau B over here, and exactly at that interface you will have a tau B as well. Remember, if you take even a smaller element over here, your shears must balance out. And as we made this assumption, since the wall is thin, this tau B stays the same throughout this thickness. If you remember, it was a solid one, then at the centroid you will have a 0, at the exterior point you will have the tau B. But if the wall is very thin, as in this particular example, if you have the wall which is very thin, the shear force on this outer periphery tau B and this small thickness that you have, it can assume to be the same. So in the internal and the exterior you have the tau B over here, right? So now that I have that this TB and TC and this tau, now if I am doing the force balance, if I do the force balance on this one, if I take a look at this element over here, the same element, all I have done, instead of representing at the shear, I cannot balance the stresses, I can only balance the forces, right? The equations of equilibrium are applied to forces, not the shear. So if I take this one, and remember it is the same thickness that we wrote down, that this is the TB and this is the TC that you have, which is exactly as you're looking at over here at this particular point, this TB, TB, TC, TC over here. So how do I write this force FB? I can write this force FB as, let me try to write that down. My force FB must be equal to force is stress times the area. So here the stress is tau b times the area will be TB and this length dx, right? So this small rectangular, thin strip kind of an area. The area is TB times dx. So the force is going to be FB will be tau b times T at B times dx, right? Similarly, for the bottom part FC, I can go ahead and write FC as it will be tau C times thickness there times dx. Now, although I have written out these forces, I must satisfy equilibrium. My total FB, which is in the horizontal direction along the x direction, must be equal to the FC. So if I go ahead and write that, so from my summation of Fx equals to 0, which is always valid, what I can write from these two equations 1 and 2, my tau b times Tb times dx must be equals to tau c times Tc times dx, right? So here my dx and dx goes for a toss. So eventually I end up with a relationship that is my tau b times Tb is equal to tau c times Tc. Now what does this expression tell you? I had taken two random points B and C, or this a quadrilateral element A, B, C, D, and what I am seeing is that the product of the shear at B times the thickness at B is equal to the product of the shear at C times the thickness at C, right? So if you consider this, all along these points B and C could have been anywhere. So all along this thin wall tube, all across the cross section of this thin wall tube that is there, the product of the shear and the corresponding thickness, remember this T varies, so I had a different thickness here and a different thickness here, I had a different shear here, I had a different shear here as well, but the product of the shear and the thickness at that particular point remains a constant. This particular guy can be approximated or can be said as a variable Q, right? With this Q that remains constant across this entire cross section, and this Q is known as shear flow. So this is very important. So let's just make it a marker over here. This Q that I just wrote over here, this is known as shear flow, right? This is an extremely important concept, and later you will see we will study this a little bit more in details when we talk about shear stresses in beams and so on. So the overall conclusion is that, let's just maybe write it down, that as long as the thickness is small, product of tau and T is a constant, and this constant is nothing but our shear flow. It's a very interesting concept which you will see later you will make a lot of use, right? Okay. So now that we have concept of the shear flow and we are beginning to understand that how these shear stresses vary when you're looking at thin wall tubes, let's go ahead and try to derive the torsion formula for the thin wall tubes. So what we are looking here in this figure is a thin wall tube with a particular thickness T. This T can be varied, but for this one we are just simplified as T, and you will see the eventual formula that we derive for the torsion formula for the thin wall tubes. This it boils down to a more simplified version. Okay. So now the question is that how do I relate the stress, the shear stress tau, with the, say, if you're taking the section, if you're applying a torque T, how do I relate to that? Similar to how we derived the torsion formula for the solid circular shaft, we took a small area, remember dA, we wrote what is the torque about the centroid point, and then we integrated that to find the entire torque. So here you see for this particular section, this dotted line that you see over here is this median line, which is sort of runs through the center across this entire cross section. So let's just maybe mark that one. So this is the median line. Okay. So let's start writing the basic expression for the moment for a small element. So if I take along the median line a small element which is of length ds, right, and say a particular thickness, then what I can write about the moment about this centroid O is that my dt due to that small element over here, which say carries a say it carries a torque of tau, right? So suppose that here it's not torque, the shear stress of tau. So suppose this element ds over here carries a shear stress of tau. So in that particular case, what we can write that my dt, or this incremental torque, which this due to the shear in this small element of length ds and maybe thickness t, what I can write for that one, the dt is going to be my tau, right, times, so first I have to find the force, then I have to multiply with the distance. So it is going to be, the force is going to be tau times the thickness t times the length of ds, right, times the distance, the perpendicular distance, that is r, right. Now from here I can maybe go a step further and I can write this as tau times t is equals to what we saw, the product of the torque and the thickness, right, is equals to your shear flow q. So it is going to be q times r ds. That is, this dt is for the small length ds, right. Now if I have to find the total torque, I have to essentially integrate over this entire median line. This ds was a small segment of this median line which I just wrote over here, right. I have to integrate about that entire length. So this tells me that your t is going to be integral of q r ds from 0 to lm, where lm is the length of the median line. So here I'm going to call this lm, right, which is nothing but length of the median line. Okay. So here, since q is a constant, we derive that q, the product of the shear stress and the thickness, is same throughout. So I can pull the q out of this equation. So q integral of 0 to lm, length of the median line, r ds, right. Now it is difficult to calculate this integral. How do we calculate this integral? This integral is when you are sort of encircling the entire median line which is there, right, and this integral is essentially calculating the product of r and this ds, and r is changing at every point, the r is changing, and if you take the small length ds along the median line, how do we calculate this integral of r of ds? Well, there is a simplified way, a geometric interpretation that we can do to calculate this integral. What I want you to do is to focus your attention on this triangle that I'm having, this particular shaded triangle that I'm having over here. Now, if you take a look at this shaded triangle, what can I write? So this shaded triangle sort of spans this length ds, as you can see, right? And it has an altitude, and the two ends are connected to this centroid O, and it has an altitude of r, which is the distance which I had used to calculate my incremental torque over here, right? So if I have to write the area of the shaded triangle, how can I write the area of the shaded triangle? So let's write. So I'm going to call the area of the shaded triangle as AS, right? So this is the area of shaded triangle. So the area of the shaded triangle is simply going to be AS is going to be half of the base times the altitude, right? We know that that's the area of a triangle. It is going to be half times ds times r, right? So your r ds, which is essentially what you have over here, r of ds is equal to 2 times as. Now try to comprehend this. So what is going to be if I take the integral of 0 to lm r of ds? What does that represent? For this small of ds over here, this r of ds is nothing but 2 times the area of the shaded triangle. Now if I'm traversing across that entire length of the median line, if I'm traversing across this entire length, it is simply going to be 2 times the area of this entire section that I have over here, the entire area with this median line encloses, which is essentially your this entire area which is inscribed by this median line over here. This entire area, it is going to be that one, right? So here is going to be 2 times the area m, where am is area enclosed by the median line. Now it is a very common mistake and I want you to make a note of it. This area is not the cross-sectional area. It is not the cross-sectional area of this thin wall that you have. It is just the area of it which is enclosed by the medial line and not the cross-sectional area. So let's make a big bold note of that. So this is not the cross-sectional area of tube. This is just the area which is inscribed, and remember it's a solid, it's a thin solid tube, so it's not the cross-sectional area of the tube itself but the area which the median line encloses, right? So now if I take this expression which I just derived, if I take this one over here and then sort of plug it back to this one, what I get is that my T becomes equal to Q times 2 am, right, which gives me further that Q equals to T by 2 am, where am is again the area enclosed by the median line, right? If you write it a bit further, Q, and now if I assume that the thickness T remains the same throughout, so you have a thickness T over here at this particular point, it has sort of disappeared behind my red line, so let me just write it again. So say this thickness T, suppose it is same throughout, this can be simplified further into writing that tau times T equals to T divided by 2 am, right? And this can be further written as my tau, that is the shear stress that I have, is equals to the applied torque T divided by twice the thickness times the area of the median line. So this is the torsion formula for the thin wall tubes, and remember this is hinged on the assumption that your thickness remains the same throughout. So this one, assuming T, the thickness remains same throughout. Right? So this is an important concept of what we just learned for the thin wall tubes, that your shear stress may be different at different points, but the product of the shear stress and the thickness at those points are the same. And if you consider the thickness to be the same throughout, this is how your tau is dependent upon the applied torque. Remember, if the thickness is the same throughout, your tau is also going to be the sort of the same throughout. So because your tau times t is a constant, right? Okay. All right, now moving on. So this was the thin wall tubes. Next is the topic of stress concentrations in torsion. Now, as you had seen for the axially loaded case, where you have discontinuities or jump in the cross-sectional areas, your stresses shoot up. Similar happens to what is in torsion. Now, if you ignore all the things which are over here, and if you just look at the bar itself, suppose you have a bar where you have a particular portion of a diameter d2, and you have another portion of diameter d1, and you have a transition in between. Now imagine if you are having a structure like this and you are applying a torque at both the ends, right? Where do you expect this to fail? You expect this to fail pretty much at these interfaces over here, right? And why does it fail there? Because the stresses shoot up over there. Now, if you take a look at these individual segments separately, for example, if you take a look at this particular segment over here, if you're applying this torque T, you will probably get a shear stress distribution like this. If you're looking at this segment over here, you will get a shear stress distribution like this over here, right? But if you're looking somewhere in between where the transition of the stresses happen, you will see that at the centers it is 0, that is fine, but at the ends over here where you are neither at d2 nor at d1, but you are sort of transitioning, you will have this peaking of the stresses because of sudden discontinuities that you will have over here. So in these regions you will have this tau max. Now remember that for the axial cases we also looked at the similar charts, right? This chart is simply tells that compared to the nominal values, how does the maximum stress look at, right? So here the nominal value is computed for this one. So these charts you can develop for, you can compute the nominal value for D2 and then you can compute that as well. But these charts are typically developed for the smaller diameter. So for this one, the smaller diameter is D1. So for this is the nominal value that you have. And all this chart tells you is that your tau max, which is happening at this interface, how it is dependent on the nominal value through this factor K. So K is sort of that amplification factor. The stress amplification factor is always higher than 1. And how it depends upon this fillet radius, right? Remember, if you have a very nice and smooth transition, then it is going to be lesser. If you have a sudden jump, the stresses are also going to jump up in those regions, right? So for different values of R over D1, if you take a look at the x-axis over here, for different values of the ratio of that fillet radius to your smaller diameter D1, you have the different values of K over here, through which if you are given a problem and if you are given this data, you can compute that by what amount the stresses at these points are going to shoot up, right? So that will help. These essentially help when you are designing sections, when you are designing, say, a member which needs to be designed as one part having a larger diameter and the other part having a shorter diameter. In those particular cases, it helps you find that what is going to be the peaking of the stresses at these interface regions that you have over here. Okay? So with this discussion on the stress concentration in torsion, remember this discussion on the stress concentration was also on, you are transitioning from a solid circular to another solid circular, just the diameter was changing, but overall more or less 90% of the topics that we discussed except the thin wall tubes was on solid circular shafts or hollow circular shafts. Remember, the hollow circular shafts are not thin wall, they have a thick wall over there, so your tau remaining constant across the cross section from the outer diameter to the inner diameter is not valid. You have a tau min and a tau max, right? But all these discussions were related to circular members. Now what I encourage you as a future topic, if you want to read, is for non-circular sections, the basic textbooks which we refer to, they do a little bit of a treatise, a fair amount of topics of things they discuss on these ones. But if you are interested, you please go ahead and take up some advanced courses in your future, like theory of elasticity. You can look at advanced solid mechanics, where you will discuss some of these problems, and you will see that how the shear stresses change. And remember that we had discussed, for the rectangular section you undergo warping, that your section is not perpendicular to the longitudinal axis anymore. And if you have other kinds of sections, for example the ellipses, the triangles, equilateral triangles, if you have a rectangle, you will see that different points have maximum shear and different points of minimum shear. So I encourage you, if you want to have some pleasure reading or fun reading, to go ahead and read on some of these topics over here. So overall, I hope that you enjoyed this chapter or this topic on torsion, which was quite different than the chapter on the axial loading. But with the thing being said, is that in between we looked at analogies in between, how these seemingly completely different types of loading causes analogically similar deformations, analogically similar your angles of twist and so on, right? So I hope overall you enjoyed this topic. In the next chapter, we'll move on to a new topic where we'll talk about the shear forces and the bending moments.